Alrighty, so we're going to go over the stuff we learned from this week about accommodation and all that. And as we get started, I want to talk about lenses and kind of what's going on with the lens within our eyes when we do accommodate. So when we're in a relaxed state, our lens is more, let me rephrase that. It's less curved. It's just kind of stretched out. And when we do accommodate, it becomes more curved or more convex. And so because of that, the light going through it is going to converge more, if that makes sense. And so when I'm thinking about accommodation, I like to also think of it as how much more power does the lens have to do to counteract the diverging light from however close that object is. So I'll say that again. How much more power does the lens need to counteract the diverging light coming from the object? So, anyways, so let's talk about an emmetrope and kind of set up a problem with someone who doesn't have any refractive error. So for an emmetrope, they can look at distance and things are perfectly clear. I gotta sneeze. They can look at something that's infinity away and it's clear. And so their far point divergence will be 1 over infinity, which is effectively 0. But if we bring an object to 50 centimeters from an emmetrope, so as we bring it closer, the focal point, or I guess where the image is focused, will get pushed back as well. So it's kind of this goes this way, that means this is going to go this way. And so if the eye doesn't do anything, it's not going to be clear. It's going to be blurry. And so the eye, or the lens, needs to do something to counteract this how it's off the retina. And so it's too far, so it needs to become more converging. So the lens is going to become more convex to counteract the divergence, the negative, or I guess the diverging light from here, in order to make it focus right on the retina. So hopefully that makes sense. So we've got this equation. I pulled it from the book. But basically, we're just going to put the far point of the given person, and that's going to equal the object divergence plus how much they're accommodating, or how much more convex their lens has become. So, as we said before, for this emmetrope, their far point is 0. All right? And so so it's 0. And then the object divergence, I went ahead and did the math, it's just 1 over 50, 50 centimeters, or 0.5 meters. And that's going to give us a negative 2 diopters. So that's the divergence of the object. And we need to find the accommodation that the eye is doing to get that object to be on the retina. So we have that first equation that I showed you guys. But yeah, just like any other equation, you can always rearrange it to solve for what you want. So I went ahead and rearranged it for accommodation here. So in order to find accommodation, I just need to take the far point divergence and subtract that by the object divergence. So let's do that here. Let me find a good color. Let me change the color. Let's do feeling fancy. Let's do this one. So we'll take the far point divergence, which is 0, minus a negative 2, which is the object divergence, and that's going to equal our accommodation. So 0 plus 2 equals 2. So an emmetrope looking at something that is 50 centimeters from them will have to accommodate 2 diopters worth. Their lens will have to become two more diopters worth of convex in order to counteract the negative 2 diopters of diverging light coming from that object. Okay, let's now talk about a myope. So, one thing I like to do conceptually that makes it just a little bit easier, and maybe that will help on the quiz as well, is you can find whatever they need to accommodate as if they were an emmetrope, and then a myope has to do 2 less than that. So if they're a -2, they have to do 2 diopters less to accommodate the same object that an emmetrope would. So let me do it as if it was an emmetrope. So I'll take let's say the far point of an emmetrope is 0, right? And we found the object divergence for this at 20 centimeters is -5. What is the accommodation that they're doing to make it clear? So as we did before, we'll do far point minus the object divergence, and that's going to give us our accommodation. So as we see here, it's going to be 5 diopters. So that's for an emmetrope. And then for a myope, just think of it, since they're nearsighted, they'll have to do however much their prescription is less accommodation than an emmetrope. So I can just think, okay, what's 5 minus 2? That's going to be 3. Oh, excuse me. +3. So, and myope looking at something 20 centimeters away will only have to accommodate 3 diopters compared to a emmetrope who will have to accommodate 5 diopters. So they'll accommodate less. I'll go ahead and do the math regularly though for myope in case someone wants to do it that way. So I wrote it up here for the far point divergence. That's the same as their prescription. So it's a -2 diopters. And then the object divergence we found earlier is a -5 diopters. What is the accommodation? So let's write it here. So far point, -2 minus a -5. And that's going to equal our accommodation. Equals, so -2 plus 5 equals, brain fart, 3 diopters. There you go. So, yeah. So you can do it that way if you want, just plug and chug. Or if you want to conceptualize it and be like, okay, if the object is, if the object divergence is -5, then the emmetrope will have to accommodate a +5. And then if they're a myope, they'll just have to do however much their prescription is less than that. Let's do it for a hyperope now. So let's say we have a +4 hyperope, and they're looking at an object that's, again, 50 centimeters away. And let's do it in the first way that I did it. So just think of it as an emmetrope, and then just add on or subtract on however much this person's prescription is. So since this is a hyperope, they're far-sighted, so looking at close things will be more difficult than for an emmetrope. Okay? So I'll just add on, because this is add, right? Add on those diopters to get the final amount that they're accommodating. So this person is looking at something that's 50 centimeters away, so I'm going to find the object divergence of that, so it's -2. And so if it was an emmetrope, they would have to accommodate a +2 in order to make it clear. And then I'm like, oh, but this is a hyperope, so I'm just going to add on 4. So they are going to accommodate 6 diopters in order to make it clear, compared to an emmetrope who will only have to do 2. And basically the math for that is this. So really it's just the opposite of whatever the object divergence is. So it's just a +2. Anyway, so there's that. But if we wanted to plug and chug using our equation and the far point divergence of a hyperope, then we'd go like this. So we'll do far point, which is a +4 diopters minus a -2 diopters Add those together, and it'll be 6 diopters. So I think either way is fine. Whatever works best for you. I personally like to think, okay, what's the object divergence, or what's the near point that they're looking at, and the divergence of that. Flip flop it. And so if it's a -2, then an emmetrope's going to do a +2. And then for a hyperope, I'll just add on their prescription, and that's how much they're accommodating. And for a myope, I'm just going to minus their prescription, and that's how much they're accommodating. So conceptually, remember, myopes or nearsighted people can look at near a lot easier because they have to accommodate less. Hyperopes, it's harder to look at near because they have to accommodate more because they're farsighted. Anyways, so there's that. And then I want to quickly talk about if someone has an add-on, like a readers. Think of it, if they have a +1 reader, think of it as they are doing however much for a +1 reader, the glasses are doing 1 diopter's worth of the accommodation for the person. And so that's just one less power, less juice that they'll have to work to get it clear. And so if I were to do the math here, and this is for an emmetrope. Should have mentioned that earlier. So for this person, if they're looking at something that's 30 centimeters away, the divergence is -3.33. And so that means that their accommodation without the add would be a +3. But since this, is doing 1 diopter's worth of it, that means that the patient, will have to do 1 diopter's less. And so I'll just -1 from that. And it'll just be 2.33 diopters. So if it was a +2 add that they have, then the patient would have to do 2 diopters less because the glasses are doing it for them. So anyways, so there's a basic walkthrough of accommodation. I will put more questions similar to Dr. Hickenbotham's questions on the Kahoot that I'm going to make. And I'm just going to have a Kahoot running and going so that by the time we get to finals, we'll have just I'm not going to do all the Kahoots for the final because that would take too long, but I'll let you guys have the one from the midterm, and then we'll do the one for the final together. But anyways, let's do depth of field or depth of focus real quick. So basically what he was trying to say is depth of field, depth of focus is the range in diopters of which something is acceptably clear. And so, for example, from here, you can't see that. From here, that still sucks. From here to here, if that object is within this range, it's still going to be acceptably clear, right? And for this person, it happens to be 1 diopter. And remember that it's in diopters. Okay, so if we look over at the depth of focus for the retina, that range is from here to here, and that distance, that depth of focus is still 1 diopter. However, the distance is 0.37 millimeters, whereas over here it's 11.43 centimeters. And so if we're ever having to do the math for it, just remember that the distance isn't the same wherever you look for their depth of field, but the diopter of their depth of field will be same wherever. Okay, so it doesn't matter if they're looking 10 centimeters from their face or 1 meter from them, that range will still be 1 diopter, though the distance or that range in meters will be different. So just think of it in diopters is what I'm trying to say. So anyways, there's that.